Awesome. We are all set. So, today's lecture is our very first on a series of lectures on machine learning. This is how we're going to conclude the course by talking about one of the hottest topics in AI. As I mentioned, we'll begin our discussion by looking into a fundamental type of machine learning models called Naïve Bayes. It's a funny name, isn't it? Why would we use any method that has the word naive in its name? Well, we'll see. So, just a quick overview of what we're going to discuss in the next couple of lectures. Up until now, we've learned how to use a model to make optimal decisions. But of course, we did talk about a bit about learning a model or model-free learning in the context of reinforcement learning. In the next few lectures, we are going to build on similar concepts. We are going to talk about machine learning and how to acquire a model from data or experience. This can translate into learning parameters like probabilities, learning the structure of the model, such as Bayes nets and the Bayes net graph structures, and learning hidden concepts like clustering and neural nets. Today's lecture is going to be on model-based classification with Naïve Bayes. Before I get into the nitty-gritty of everything, I want to discuss the concept of learning and machine learning at a very high level for a little bit. Now, to begin this discussion, I want to start by looking at the word learning. Of course, learning is not limited to machines. We, human beings, as natural instances of intelligence, also learn. But what does that mean? How can we define the process of learning in concrete terms? I need volunteers to give me examples of things that we learned before we were 5.
Walking.
Shantanu, that's a good example. Walking. Any other examples?
Eating food.
Venkatesh?
Learning language. Mother
Talking,
tongue.
yes.
Yeah.
That's a very good example. Any other examples? So Shantanu mentioned eating. Venkatesh?
Habituating going to school.
Before 5, yeah, going to school. Any other examples?
Learning.
Ramu?
Making missionary parts, learning how to make the missionary parts or something.
I'm sorry, I didn't catch that. Did you say visionary part?
Yeah, missionary, like missions.
Missions. Can you tell me more?
Yeah, making you can call that for car parts. We humans making with the hands, but if you learn a robot individually, then it can make its own.
Okay. All right. Thank you. Shantanu?
Learning what is hot and cold.
Learning the concepts, learning the meaning of words, learning the mapping between the words and their realization in the environment around us. That's a very good example. So what do all of these examples have in common? Walking, talking, eating, mapping concepts, going to school. All of these words have a very, very interesting string of characters in common. ing, ing. All of these are verbs, right? Now, can you think of a mathematical equivalent for verbs? How would we translate, how would we represent verbs into mathematics? Satvika?
Whether it is done or not.
Whether it's done or not. So your proposal is to use if statements.
Yep. Zero, as in 0 and 1. Yep.
Okay. What I'm looking for is more in the line of what sort of mathematical structure or operator would be suitable to represent verbs. Shantanu?
The action.
Well, verbs are actions, right? But how do we represent actions in mathematics?
If it is an example of a running car, then if it moves, then it is an action. So acceleration is the point of action in that thing.
I'm looking for something a little more abstract, but thank you. Venkatesh?
Is it like equations?
A little more fundamental. So I'm going to suggest an answer. How about functions? What do you think about modeling verbs as functions? I think it's a suitable representation. So if we decide to represent verbs, things that we learn, as functions, what would be the process of learning in mathematics? A suitable answer, in my opinion, is function approximation. Figuring out what the correct function is from observations and experience. With that logic, we can summarize learning as the process of function approximation. And the same can apply to machine learning. In machine learning, we want to approximate a function that describes a particular verb, a particular process, with the highest amount of accuracy. What do we have to fuel this process? What does this process run on? It's data. It's observations, experiences, and such. Does anyone have any questions about this equivalency and this analogy? Does it make sense to everyone? Okay. Now, with that introduction, let us dive a bit deeper into technicalities. Machine learning comes in different types and categories. One subclass of machine learning tasks is the classification task. It's a task of assigning labels, telling different entities apart in the input data. Let's look at an example of that. Spam filtering and spam detection is a binary classification task. What do I mean by that? The task of spam filtering is essentially that of telling a spam email apart from a genuine or ham email. Ham is the opposite of a spam in the domain of a spam classification. So a good email is considered ham. Why is it a classification task? Because we are assigning a label. We are assigning a class to each email. We're saying this email belongs to the class spam. The other email belongs to the class ham. Now, let's talk about the settings of the spam classification with regards to machine learning. It's what's the input to the system, an email. What's the expected output, the determination of whether the email is a spam or ham. Now let's look at a few examples. These are examples from a real data set of emails. I believe it's from the Enron email data set. You can probably find it online. I know some of you are working on spam detection as your final projects. Now, let's read through the first email. Dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret. Now, if you believe that this email is spam, please raise your hand. Okay. One person believes that it's spam. Two people. Anyone else? Is anyone voting for this email being spam, the very first one? Now, okay, we have 3 votes for this email being spam. Now, if you could lower your hand. Great. Now, who here believes that this email is ham or genuine? Two. We have 2 votes. Very well. Lower your hands. Who here does not know whether it's a spam or ham? 1 person. 2, 3, 4, 5, 6. Very well. Lower your hand. Of course, in a typical classroom, I would also ask who here doesn't care whether it's a spam or ham, but let's forget about that for now. Now, Kuntong, I believe you raised your hand. You voted for this email being spam. Would you like to explain why you think this is a spam?
Yeah, spam. The spam usually have some format. It look like a spam.
It looks like a spam. Can you be a little more specific? What in the text of this email makes you think it's spam?
Because usually when people send an email, they not begin like this. I never received. Yeah.
Yeah, that's a very good observation. So yes, this is a spam. I'm going to put Kontong on mute. Why is it a spam? How can we tell this is a spam? Think about it for a little. Let's look at another example. The second email. To be removed from future mailings, simply reply to this message and put remove in the subject. And then 99 million email addresses for only $99. Who here believes that this is a spam? Raise your hands. Okay, and who here thinks that this is ham? First of all, everyone lower your hands. Who here votes for this email being genuine? Okay. We have 1 vote for genuine and many more votes for spam. Satvika, you voted for spam. Can you share your observations and thoughts on why this is a spam?
Usually, all the letters in a mail doesn't consist of all uppercase letters. And
That's a very good observation. Yes, and
moreover, if like if for any genuine mail, for removing the remove in order to not get these kind of mails, they will be having a unsubscription URL.
That's a good observation. That's a very good observation. Thank you. So yes, this is indeed spam. Let's look at the last one. Okay, I know this is blatantly OT, but I'm beginning to go insane. Had an old Dell Dimension XPS sitting in the corner and decided to put it to use. I know it was working pre being stuck in the corner, but when I plugged it in, hit the power, nothing happened. Who here believes this is a spam? Nobody? And who here votes for this being ham or genuine? Okay, a good number of you. Very well. Thanks. You can lower your hands now if you want. Yes, this is ham. Now you can see it's actually not that straightforward to determine whether an email is a spam or ham. In the first two instances, there were some disagreement on whether a particular sample is ham or spam. We want to use machine learning to solve this problem, the problem of determining whether an email is a spam or ham. What's the setup? What's the typical setup for solving this problem? Well, first we get a large collection of example emails, each labeled as spam or ham. Now, note that someone has to hand label all this data. This is very important to keep in mind. For this type of setting, there is always a requirement for some manual labeling. Or, of course, the labels may come from the environment itself. We will talk about examples of that later. But there is some label for your sample. You know what the correct class for each sample in the large collection of example emails is. And we want to learn to predict labels of new future emails. This is really important. We have a large collection of example emails. We want to learn to predict labels of new future emails, emails that we have not seen. So we want to learn a function that generalizes well to unseen data. This generalizability is very important. We will keep coming back to this keyword throughout this lecture and the coming lectures. Now, what are the features? Well, first of all, what's a feature? Features are the attributes, the set of attributes used to make the ham-spam decision. What can we use as these attributes or features? It can be words, like the word free is probably a good indicator of the email being spam. Like text patterns, it was mentioned in our discussion that all caps is probably an indication of email being a spam. Or non-textual features, such as whether the sender is in contacts, whether the email has been widely broadcast to many different recipients, and so on. Let's look at another example of classification. This is essentially the hello world problem in machine learning these days, especially in deep learning. It's that of handwritten digit classification. There's a data set called MNIST, M-N-I-S-T, which contains a large collection of images or photographs of handwritten digits. And the idea here is to learn to predict labels of new future digit images. These are some samples of what we have in that data set. We have a sample of this shape. Well, it looks like a 0. So let's say it's a 0. This one looks like a 1. So let's say it's 1. This one looks like a 2. Let's say it's 2. This one again looks like a 1. Note that this is not very similar to this one, but we can still, as instances of natural intelligence, determine that it's probably 1. What about this one down here? it's not very clear, right? We want a good model that's able to determine what this digit is as well. What's the setup here? Again, similar as before, we get a large collection of example images, each labeled with a digit, with the corresponding digit. Again, note that someone has to hand label all this data. And as I mentioned, we want to learn to predict labels of new future digit images. What are the features here? What features can be used to represent these examples? We can look at pixel values, right? These are black and white images. We can use pixel values, which are binary in black and white, whether a particular pixel in the image grid, like pixel, the pixel in row 6 and column 8, whether it's on or off. We can look at shape patterns, like number of components, like aspect ratio, like number of loops. We can look at other features as well, and note that features are increasingly induced rather than crafted. So can anyone here think of other features that we can use to represent these images? Anyone? Any thoughts? Any guesses? Okay, think about this question. We're going to come back to it when we get to neural networks next week. So these were two very simple examples of classification tasks. But classification is essentially the major portion of commercial AI technology out there today. What's the task? As I mentioned before, given input X, predict the labels or classes of that input Y. What are some examples of this? For example, we can talk about medical diagnosis. The input is a set of symptoms, and the output or classes are different diseases. Fraud detection. This is an iffy example because fraud detection can be classification or other types, such as anomaly detection. But if it's classification, the input can be account activity and the output can be fraud or no fraud. Automatic essay grading. This is very interesting. Gradoscope, the web service we just started using for our quizzes, provides an automatic essay grading service where the input is document and the classes are different grades. Customer service email routing. Imagine you're working at a customer service department in a company, an email comes in asking about a particular thing, and you want to be able to know which sub-department or which person is best to respond to that question. Like if you imagine professors at our department all being customer service reps with regards to your questions, if you send in a question about AI, a classifier should be able to determine that the questions regarding AI should go to the professor teaching the AI course, not the professor teaching, for example, C programming. Sentiment analysis, language identification, for example, you given a text in some language and the classifier should be able to identify the language of that text. Why is it useful? Well, this can be the first step of translation, automatic translation. If you go to Google Translate, when you paste in a foreign language, it automatically determines the language. Classification, as I mentioned, is an important commercial technology. A lot of the money in AI is currently invested in classification models or classification tasks. Now, remember when we were talking about reinforcement learning, we talked about model-based and model-free reinforcement learning. Today we are going to focus mostly on model-based classification, which is similar to model-based reinforcement learning. In the sense that in model-based classification, we build a model such as a Bayes net where both the output label and input features are random variables. Then we instantiate any observed features and query the distribution of the label conditioned on the features, conditioned on the observation. We've already seen this setting, right? We've already seen how inference can be made in Bayes nets. Now, the important part in here is building a model based on observations. What are the challenges here? What structure should the Bayes net have if you're going with a Bayes net model? And how should we learn its parameters? So this entire lecture is going to focus on answering these two questions. So we're going to begin with one class of Bayesian approaches to classification as a machine learning task, and it's called Naïve Bayes. Naïve Bayes assumes that all features are independent effects of the label. What does that mean? Let's think about it in terms of simple digit recognition. The MNIST example we looked at in a few slides ago. So we can assume that each grid position is a feature, and feature values are on or off based on the intensity on the ink, based on whether the intensity is more or less than 0.5 in the underlying image. If it's not grayscale, if it's just black and white, you can forget about the intensity. If you see black, it's on. If you see white, it's off. And each input maps to a feature vector. So a feature vector for this particular image can be in the form of, well, the feature for grid 0, 0 is 0, it's off. For grid 0, 1 is 0. For grid 0, 2, it's 1. It means that at grid 0, 2, at row 0, column 2, something, the pixel is black, so it's 1, and so on. This is called the feature vector. Now, we have lots of features, and each is binary valued in this example. The Naïve Bayes model says that the probability of a particular label, and what are the labels here? Digits, 0, 1, 2, 3, 4. Conditioned on these features can, of course, be inferred from the probability of the label as a random variable, multiplied by the multiplication of all of these features. This is essentially Bayes net under conditional independence, right? Now, let's go back to our very first question. Why do we call this Naïve Bayes? It's because of this assumption, right? It's assuming that all features are independent effects of the label. Now, we know that this is not necessarily the best assumption. This is a relatively hard assumption. There can be correlation between individual pixel values, right? But this naive assumption, the naivety of Naïve Bayes, can still work to our advantage. It simplifies things for us. We are assuming that all features are independent effects of the label. So we can simplify this conditional probability into this factorization. What do we need to learn here? Which of these parameters is not known and needs to be estimated? Let's see. A general naive Bayes model, as we mentioned, can be represented as such. The joint probability distribution of the label and the features is given by the probability of the the label random variable multiplied by the probability distribution of each feature conditioned on the label. So let's look at how many different values there can be. There can be the number of different values is essentially the number of different labels that we have, the size or the size of the domain of the label random variable, multiplied by the number of features and not the domain of each feature to the number of features, this n here, which can be relatively large for this representation here. Now, if we apply the naivety assumption that features are independent effects of the label, then this can translate into this simplified representation, which only requires n number of features times the domain of each feature. In the image, in the digit classification task, it was 0 or 1, so this is 2, multiplied by the domain of labels. How many different classes do we have? Which in digit classification is 10. This is clearly much smaller than this, right? So this naivety, this hard assumption, is simplifying the computational aspects of modeling digit classification using Bayes nets. So we only have to specify how each feature depends on the class. That's all we need to specify. And the total number of parameters, as you can see, is linear in n. Of course, the model is very simplistic. It's interesting to know that it often works anyway. In many practical situations, including a spam classification, it's still very effective and, of course, cost efficient. It's surprising, but it's true. Now, let's talk about inference for naive Bayes. What's the goal here? The goal in classification using naive Bayes is to compute posterior distribution over label variable y. So what's the first step? The first step is to get joint probability of label and evidence for each label, right? So for label 1, we get the joint probability over different feature values. For label 2, all the way to label k, which under the assumption of conditional independence on labels translates into the simpler form of p of the label, the probability of this particular label occurring, multiplied by the multiplication of the probability of each feature occurring conditioned on this label. This should be very straightforward if you remember our previous discussion on Bayesian networks and inference. Now, if you sum it up, sum all of these up, this essentially gives us the probability of evidence, the probability of seeing the particular sample that we want to classify, right? And the third step in inference for naive Bayes is to normalize. How do we normalize? We just divide step 1 by step 2. And that's all we need to do for inference. There's nothing new in terms of methodology and technique in the inference stage of naive Bayes. But what do we need in order to use naive Bayes? Inference method, We just saw this part. We start with a bunch of probabilities, like the probability of the labels and the probability distribution of each feature conditioned on labels. And then we use standard inference to compute the probability of labels conditioned on the features or the observations. And there's nothing new here. We've already seen all of this. The next step, the next thing that we need is the estimates of local conditional probability tables. Remember, local conditional probability tables was the core, was the nut inside the nodes in a Bayesnet, right? So what do we need for local conditional probability tables? We need P of Y, the probability distribution of labels, which is the prior over labels essentially. And then we need the distribution of F sub I conditioned on Y, the random variable for labels, for each feature, the evidence variable. These two parameters are collectively called the parameters of the model. And in general, whether you're looking at a naive Bayes model or a neural network model, the parameters of the model are denoted by the letter theta. It's important to keep this notation in mind. We are going to encounter it over and over in machine learning. So the parameters, the learnable parameters of the model are denoted by theta. Up until now, you assumed that these parameters appeared by magic, right? Let there be parameter py. That's what we assumed. But they typically come from training data counts. So they don't appear by magic in practice. We actually have to look at a data set to estimate these parameters. We'll look at this in a few slides. Let's look at an example. Can you all see this example here clearly? Can you all see that this is a 3? If yes, raise your hand. What about the rest of you? Can you see that this is a 3? All right. Thanks. You can lower your hands now. So what's the first parameter that we need to estimate? Let's go back. The prior over labels. Let's see. So we are going to start with this estimate that all labels are equally probable. All labels are equally probable. This is just an initial estimate that we make, an initial assumption that we make about the probability distribution of labels. So it's equally likely to see 0 as it's likely to see a 1 if we take random samples from the data set. That's what this table is telling us. What else do we need? Well, let's go back and see. We need the probability of each feature conditioned on the label or the evidence variable. All right, let's see how we can construct this. We have, for example, P of F at row 3, 0, 1, 2, 3, and column 1, 0, 1, so this pixel here being on, conditioned on Y. Let's see, Y can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and then we have these probabilities for this pixel being on for each of these classes. I want you to think about this. Shantanu, do you have a question?
No, Professor.
All right, all right. I just saw that your hand was still raised. Very well. So where do these probabilities come from? You already know the answer, but think about it for a little while. We'll discuss this in depth soon. Now let's look at another feature. So the probability of this feature being on, conditioned on different labels, well, you see that we construct a similar table for this particular feature, and so on. Let's look at an example for applying naive Bayes for text, for example, a spam classification. There's an approach called the bag of words naive Bayes. What are the features in this approach? They are designated by W sub I, which is the word at position I. So this is a random variable representing the word at position I. For example, the word at the very first word would be W sub 0. The second word would be W sub 1. And the last word would be W sub n. As before, we want to predict label condition on feature variables. We want to predict spam versus ham, for example. And as before, we assume features are conditionally independent given the label. What does that mean? Is this a valid assumption? Well, let me see. This is essentially telling me that, let me bring up a blackboard. Actually, no. Let me go back to the original example over here. This is essentially telling me that the probability of this word, the second word in this text being B, is independent of the probability of the first word being 2. Now, can anyone see an issue here? Are these two really independent? How many of you believe that these two are independent of each other? The fact that we see the word be here does not have any dependence on whether the previous word was 2 or not. How many of you believe that there is independence between 2 and B? Nobody? How many of you believe that there is dependence between the second word being B and the first word being 2? 3? 4? Satvika, would you like to share your thoughts on this with the class?
Normally, if we are writing a sentence, so the second word depends on the first word normally in any language.
Yes, that's a very good observation. So there is dependence. Let me swap these two. All right. There is dependence between different features in actual text. But now we are applying this naivety assumption that features are conditionally independent given label. Okay, we are losing out on a lot of information here, but remember, it still works to some degree in practice. It's interesting. What's new here in the setting of bag of words naive Bayes? Each W sub I is identically distributed. What does that mean? Let's think about it for a second. What does the word identically distributed mean? Anyone? You should know this from the previous lectures. It essentially means that the occurrence of a particular word in W1 is the same as the probability of occurrence of that word in W2, and it's the same as the same measure in W3 and so on. It's assuming that each W sub I is identically distributed. All right, this is a very hard assumption. With all of these assumptions, what are we trying to do? We are defining a generative model. We are essentially factorizing or simplifying this joint distribution of P of label and features to P of labels, the prior over labels, multiplied by the probability of W sub i's given Y. This is a very, very efficient simplification. Now note that W sub I is word at position I, not the ith word in a dictionary of all the words. This is a common confusion when you later on get to review these slides for preparing for exams and assignments and such. These are just position, the word, this random variable represents the word at position I, not the ith word in the dictionary. Okay. Now, usually each variable gets its own conditional probability distribution represented as P of F condition on Y. However, in a bag of words model, each position is identically distributed, and all positions share the same conditional probability P of W given Y. This is what this assumption here means. Each W sub I is identically distributed. Why do we want to make this assumption? Any thoughts on that? Well, because it relieves us on sensitivity to word order or the length of the text, right? Now with this assumption, the ordering of the words or the length of the text is no longer important to us. The model created based on these assumptions for words is called bag of words because the model is insensitive to word order or reordering. It's like you put all the words in a bag and you just look at them without ordering. Okay, now let's look at an example of how we apply this model. We mentioned that we simplify the model to a bag of word naive base represented as such, the prior over labels, and the probability of W sub I given Y. What are the parameters? The parameters are, well, first the prior, then the probability of the word occurring in spam, and the probability of the word occurring in ham, or conditioned on the email being ham. This is very simple, isn't it? This is because we are not considering the ordering or position anymore. Let's see what an example would look like. So let's say we look at our data set and see we have 66% of the samples being ham and 33% being spam. Now, the probability of the word they occurring in spam is measured as 0.0156. The probability of 2 occurring in spam is measured as 0.0153, and so on. Now let's look at the same, but for the probability of each word occurring in ham samples. V occurs at 0.02102, occurs at a probability of 0.133, and so on. Now, here's a very important question. Where do these tables come from? I've already hinted at the answer, but I want to hear your thoughts on this. Where do we get these values? Shantana?
From label data.
I need a little more detailed answer. What's the mechanism for finding these numbers, for finding these probabilities? Ramu?
Maybe a set of words that we are analyzing.
Okay, tell me more.
The statement or sentence. Like if you got any sentence, we are finding the probability from that sentence being a spam or ham.
And how do we find that probability?
Yeah.
Does anyone else want to chime in here? Satvika?
We are calculating it from the predefined data, like the data which we have labeled already, whether it is spam or ham.
So how do we calculate it? What's the procedure for calculating these values?
So whether if it is a spam, if it is labeled as spam, then we count all the words and we count the
Yes, that's a keyword. That's a keyword, counts. So these are essentially counts. Imagine we have 100 emails in our data set. We count the number of ham samples in the data set. We see 66 of our samples are ham and 33 are spam. So the probability of a random sample picked from that data set being ham is 66%, and the probability of a random sample being picked from spam is 33%. What about these probabilities here? So we look at the number of times the word "the" has happened in spam emails, right? Does that make sense? Any questions about this? Because this is very fundamental in moving forward. All right, let's look at an example. So we start with the prior. We count the number of spam samples and ham samples. This is prior over labels. What's this over here? What are these two values? How can we have a negative value here? These are probabilities in the log scale. Why are we looking at log scale? Because as we move forward, these probabilities become very, very small, and we don't want to deal with very small values. We want to have manageable values. So 0.33 in the log scale becomes minus 1.1, and so on. Now let's look at the word Gary. The probability of the word Gary happening in a spam is measured to be 0.0002. And the probability of it occurring in ham is measured as 0.0021. And you can see the log scale measurements as well. What about the word wood? We expect it to be higher in both classes, right? We measure it to be 0.00069 in spam and 0.00084 in ham. What about the word you? This is interesting. Seems like from the data available to us that the probability of seeing the word you in the spam is much higher than the probability of seeing the word you in ham. Interesting. You might want to think about why this is. Does this make sense? And so on. These are some other samples, like the probability of seeing the word wait in spam is much higher than seeing it in ham. It may have to do with weight loss advertisement sent as a spam to the mail server, and so on. Now, it's interesting. I'll come back to this point. How do we train a Bayes model, or how do we train and test a machine learning model in general? I'm going to give you a very broad overview here, and then we'll go into the specifics in the coming slides. The training and testing procedure of machine learning models has three main components. First, there's training, where the model looks at training data and tries to learn or find a good function. Then the model assesses itself on validation or holdout data, something similar to practice exam, like what you do before taking an exam. You solve practice questions. And then to measure the actual performance, to measure how well the model has learned throughout this process, it will take a final exam on unseen questions, on unseen data samples. This is the general procedure for training machine learning models, not just naive Bayes, in general. Keep this in mind. We'll come back to this in more detail, both in today's lecture and next week's. Now, what's the idea in training? It's the base idea in training of machine learning models is empirical risk minimization. What does that mean? We want the model, like the classifier or other types of model, that does best on the true test distribution. But we don't know the true test distribution. We don't know what the distribution of all possible samples in the real world look like. So we pick the best model on our actual training set. We have some representation, some sampled representation of the true data set. That's the best that we can do. And we find a model that does very well, that performs very well on the training set, on that sampled distribution. Finding the best model on the training set is phrased as an optimization problem. So we want to optimize the parameters of the model such that the error or the difference or the distance between what the model does and what happens in what has actually happened is minimized, right? We'll go into this in more depth in a few slides and in the next lecture. So the process of training is essentially an optimization problem. We want to maximize, for example, accuracy or minimize error. What's the main worry here? The main worry is overfitting the training set. What's overfitting? I found this representation of overfitting just a few months ago, just a couple of months ago, and I think this is the best way to explain overfitting. Overfitting is when your model does really well on the training set, on the samples available in the training set, but it doesn't perform well on unseen data points. So it's like creating a mattress that fits this position really well, but then the person is not able to go a little bit to the right or a little bit to the left. That's overfitting. Now, overfitting can become better with more training data, where there is less sampling variance, or training is a lot, the training set is a lot more like the actual or true test distribution. It can also be made better if we limit the complexity of our hypothesis. I know this is a bit vague, but just keep this in mind. We're going to talk about regularization and limiting the hypothesis space later on in these lectures. Just keep the main takeaway from this slide is, first of all, the training process is an optimization problem. And second, the training process is prone to overfitting. And whenever you think of overfitting, think of this image here. All right? I'm going to re-emphasize on the word generalization. We want a model that learns from limited data, but applies or generalizes to unseen data. Otherwise, we would just use a lookup table. We don't want to use a lookup table. We want to learn a model that can be applied to unseen instances. That's what machine learning is all about, generalization. So let's look at some important concepts and terminology in machine learning. First of all, the fuel of machine learning, what machine learning runs on, is data. For classification, the data should be in the form of labeled instances. For example, a set of emails, each marked as spam or ham. Now, this data must be broken into three subsets. One is the training set, which is used by the model in the training process. Then there's the held out or validation set, which is similar to practice exams. And then there's a test set to see how well the model generalizes. We'll talk about the validation or held out set a bit more later on. Features. Features are attribute value pairs which characterize each X. So we have a bunch of words in an email. How can we represent it in a way that is mathematically usable? We can use it in a mathematical optimization process. The representation of the actual samples in a way that can be used in the training and testing of machine learning models is called featureization, or those representations are called features, which are essentially attribute value pairs which characterize each sample. And then there is something called the experimentation cycle. First, in the experimentation cycle of machine learning models, the model learns parameters such as model probabilities on the training set, then tune hyperparameters on the held out set. What are hyperparameters? Just a brief definition of hyperparameters. Hyperparameters are parameters in the model that are selected by us, the designers, the engineers of the model. They are not learned, they don't come from the data, they are selected by us. So those parameters, like, let's say, we'll see examples of hyperparameters in just a few slides. Those hyperparameters or design choices are tuned during validation on held out data or validation data. Then we compute the accuracy, how well the model performs and generalizes on unseen data using the test data set. It's very important to never peek at the test set during training and held out data. Why? Because if you know what the final exam looks like, you're not going to do well on learning about all possible concepts. You'll just focus on the questions that you've seen in the final exam, and you can't test how well your knowledge applies to unseen questions, right? Now, how do we evaluate machine learning models? There are various metrics for evaluating machine learning models and the performance of machine learning models. One is accuracy, which is the fraction or the ratio of instances predicted correctly over the total number of instances. This makes a lot of sense, right? But it's not the best metric. There are other metrics that we'll look at later on when we get to perceptron, logistic regression, and neural networks. Another concept that we've already discussed is overfitting and generalization. We want a classifier which does well on test data, right, on unseen instances. Overfitting is fitting the training data very closely, is when the model fits the training data very closely, but it does not generalize well to unseen data points. Remember that image I showed you, this image here? This is overfitting. It fits one particular position really well, but is not able to support other positions that you may have when you lie down on your bed. We will investigate overfitting and generalization formally in a couple of lectures. We'll also address it a little bit towards the end of this lecture as well. Before we get into this, does anybody have any questions? Are we clear on everything we've covered so far? All right. So let's talk about generalization and overfitting a little bit. Imagine that we have this data set. These are essentially data points in 2 dimensions. And we want to fit a function to these data. Remember, machine learning is all about function approximation. We want to find a function that best fits this data. Well, we can go with a simple linear approximation, like let's say something like this, and imagine this is a straight line. We can go with a degree 2 approximation, something like this. We can go with a degree 3 or more approximation, something like this. As you see, the higher the degree of the model becomes, the polynomial that we use to describe, to fit to this data point becomes, the more accurate it can become. However, let me erase everything. If we go with a polynomial of degree 15, it fits the data very well, right? It fits the data super well. But what happens if we add another data point here, like here? Then it's not going to capture that data point very well. It's not going to be able to fit unseen data points very well. This is the underlying mathematical issue that we call overfitting. Are you all clear on what I mean by polynomial and degree 15 polynomial? Can anyone here tell me what the phrase degree 15 polynomial mean? So this is a polynomial of degree 2, like cx2 plus dx2 plus x plus b. This is a polynomial of degree 2. Why is it a polynomial of degree 2? Because the highest power of the variable, the unknown variable, is 2. What does a polynomial of degree 15 mean? As Ayad mentioned in chat, it means a polynomial where the highest power of x, the largest power of the unknown variable, is 15. And as you can see, it may provide a very good fit to the seen data, but doesn't leave much room for unseen data. Why do we need to account for unseen data? Well, because what we have here, what we typically have in training sets is a sampled representation of the true distribution of data, right? As we discussed before. So the sampled representation that we call training set may not be the most accurate representation, the most accurate representation of the true distribution of data. Do we have a question? Is everything clear? I'm hearing some noise over the call. Let's continue. Let's look at an example of overfitting. Remember this? Can you all see this 3 here? Raise your hand if you can. All right. Now note that there is also this pixel here, which is on, and it has nothing to do with this digit being 3. So let's look at this. Let's look at P of features, where the condition on class, or the joint probability of features and class being 2, so this digit being 2, and the joint probability of features where this digit or the class is 3. So the probability of class being 2 is 0.1, the same as the probability of the class being 3, because we are assuming that each class is equally probable, and we have 10 classes, 10 different digits. Then the probability of this pixel being on, given the class is 2, is measured to be 0.8, and the probability stays the same for this particular feature for class 3. Now for class 2, this particular pixel being on has a probability of 0.1, but for 3 has a probability of 0.9. The probability of this feature being off for 2 is 0.1, for 3 is 0.7. Now let's look at this one here. The probability of this pixel being on for the digit for the class being 2 is 0.01, because there may have been a few samples, but in our data set, we have not seen any samples of the digit 3 where this pixel value is on. So we estimate this probability to be 0. Now, do you see the problem of overfitting here? 2 wins. If we pass this sample into a model that has these sort of probabilities, that model is going to recognize this sample as 2, which is wrong, right? Why did that happen? It was because of this pixel here. A single pixel ruined our model. Why? Because our model did not account for the fact that there may be samples of 3 where this particular pixel is on. We did not, the model does not account for that possibility. And this is a very good instance of overfitting. We're going to look at another example of overfitting in spam or ham. So the posteriors can be determined by relative probabilities. Like the probability of a particular word being ham over the probability of a particular word being spam, or the other way around. Now, if we think about this, we expect the word, let's say, free, to have a much lower probability, much lower ratio. Why? Because the word free, we expect to happen a lot more in spam than in ham. So we expect this ratio to be large. what's going to be the largest, which word is going to have the largest value of this ratio? What do you think? Which word happens a lot more in ham than spam? Well, specific names, Ramu.
The.
That's a very good example, but the also happens a lot in spam, right? Let's think about this one here. Which word happens a lot more in spam than in ham? Something like dollar, something like free, something like Shantanu.
Win.
Win, yeah, that's a very good example. So we expect the highest values in the corresponding table of this ratio to belong to words like dollar, buy, free, weight, Viagra, and such, right? But that's actually not the case. If we calculate these ratios, we'll actually see that the highest values are infinity. Why does that happen? It's because the denominator for particular words can be zero. For example, the word screens may have never happened in a ham sample. That's why this probability is seen as zero. So this is a division by zero, and this becomes infinity. What went wrong here? I want you to think about this. Let's take a 10-minute break and come back to discuss your thoughts and ideas on this afterwards. If you have any questions, I'm going to be available in the next 10 minutes to answer. If you have any questions before we continue with our discussion, it's a good time to ask. Very well. If you're here and can hear me, can you raise your hands? What about the rest? All right, so let me set things up. You can lower your hands if you want. I'm going to set the screen up, make sure that participants are all here. Let me load up the chat box as well. We are all set. Now, Shantanu, did you have a question you wanted to ask?
No, Professor.
Very well, thanks. I saw your hand was up. Okay, so going back to this example, we saw that we got very odd values for these ratios. And this can lead to highly inaccurate naive Bayes models for spam classification. What do you think went wrong here? Does anybody have any thoughts on this? Hint, I've already given you the answer. Why are we getting these infinity values? Satvika?
The probability of that word in that spam mail maybe like it's going towards 0.000 something.
Well, you're almost correct. Ramu?
Yeah, Professor, like the probability of getting the word in spam is very negligible, which is equal to 0. So that is the reason we are getting infinity rather than.
You're also very close. So it's not very close to 0. It's actually 0. It's possible that we never saw the word screens in a ham email, right? That's why we counted the probability of seeing the word screens in ham to be exactly 0, not close to 0. And this is messing up our relative probabilities. So what can we do? Think about this, and then we'll talk about it a bit more towards the end of this lecture. So the relative frequency parameters will overfit the training data. Like in the example of digit recognition, just because we never saw a 3 with a corner pixel on during training doesn't mean we won't see it at test time. It's unlikely that every occurrence of the word minute is 100% in the spam. And it's also unlikely that every occurrence of the word seriously is 100% in ham. These are based on those infinities that we saw in the previous slide. What about all the words that don't occur in the training set at all? In general, we can't go around giving unseen events 0 probability, right? This is very important to keep in mind. And then later on, I'll introduce a solution that takes this advice into account. As an extreme case, let's think of what would happen if we were to use the entire email as the only feature, right? So just looking at just having a single feature, and that feature is the entire email. What would happen if we were to train a naive Bayes model on it? It would get the training data perfectly. So the model would be 100% accurate on the training data. But it wouldn't generalize at all. Why? What happens if we give a new email, an unseen email to this model? The only feature that was used in this model was the entire email, the entire text of the email. What happens if we give it another sample where only one word in the text is different? The model wouldn't generalize at all, right? Just making the bag of words assumption gives us some generalization, but it isn't enough, as we saw in the previous slide. To generalize better, we need to smooth or regularize the estimates. Now, to talk about these two, I need to first talk about parameter estimation. It's essentially the act of estimating the distribution of random variables, of a random variable. There are two ways of going about this. One is elicitation. You can ask a human. You can ask a human to give you an estimate of to give you the distribution of a random variable. Why is this hard? Any thoughts on this? Well, first of all, because humans don't always have the exact distribution of a random variable, and they make mistakes as well. Secondly, asking humans to provide individual distributions for each random variable may be very tedious if you have many, many different features. So it's not economically feasible. It takes a lot of time for a human expert to provide those distributions. What's the second approach? So far, we've talked about elicitation. The second approach is empirically. The model can use the training data to estimate the distribution of a random variable. And this is the essence of learning. This is the essence of machine learning. For example, for each outcome X, look at the empirical rate of that value. Let's look at this example here. Imagine that there are two possible outcomes, blue and red. There's a bag with two types of marble, blue marbles and red marbles. And you want to estimate the distribution of the marble being red versus the marble being blue. You pick 3 samples from the bag. The first sample is red. Then you pick another sample. The second sample is also red. And then you pick a third sample. The third sample turns out to be blue. So how can we calculate the probability of the outcome of this random sampling being red? Well, it's essentially the count of how many times we observe red in our samples over the total number of samples, right? Which is, for this particular sample, 2/3. This is the estimate that maximizes the likelihood of data. And we represent it as the likelihood equation, likelihood of X, the outcome X, given model parameters theta, is equal to the multiplication of all X's given the model defined by parameters theta. This is called the likelihood of data, and this is relatively simple and straightforward to understand. Now, let's talk about maximum likelihood. It turns out that the relative frequencies are the maximum likelihood estimates. So let's look at this bit here. The parameter, the model parameter is theta, that we want to find the model that gives us the maximum likelihood, right? That gives us the best estimates of probability distribution. Those parameters can be found through a maximization of this form. We want to find the parameters theta that maximize the probability of outcome given theta. Okay, what does this translate into for naive Bayes? It's essentially just argmax over theta of multiplying all probabilities given theta of the potential outcomes. So far, I hope this makes sense. Any questions? All right. So in empirical parameter estimation, or in other words, in machine learning, the probability, as you can see here from this multiplication, of an outcome X is given by the count of the number of times we see that outcome over the total number of samples that we are looking at. Another option is to consider the most likely parameter value given the data. Okay, what does that mean? So the most likely value, the most likely, the parameter that gives us the most likely value can be calculated using this optimization formulation. We want to find the theta that maximizes this probability, the probability of theta given the outcome. Okay, this should be very helpful. Why? Because then we can look at what the outcome, what the distribution of outcome is like in our training set, and then infer the parameters that give us the maximum likelihood. So let's factorize this. P of theta given x, remember Bayes' rule, is essentially P of x given theta multiplied by P of theta over P of x. All right. Now this P of x, these priors, are essentially a constant. They don't really matter. We can just simplify this into argmax over theta of P of x given theta multiplied by P of theta. Okay, now how can we solve this? We aren't going to go over the mechanics of finding or solving this optimization problem in this lecture. We'll talk about this in a lot more detail in the next lecture. But you can see that it's relatively straightforward. There, but just looking at the data set, it's still possible to fill these values and find the maximum. I'm going to add a little more detail in a couple of the slides. What about unseen events? Remember, we are making all of these inferences based on seen samples, based on the observations available to us in the training set, right? What about unseen events? Imagine that every day you wake up and you see that the sun rises in the east. So for the past million years or 2 million years or so, every day we've observed that the sun rises every morning in the east. But what happens if one day we wake up and we don't see the sun rising in the east? How do we account for something that we have not experienced yet? How do we account for data that have not been observed yet? In other words, data that do not exist in the training data set. So one solution is proposed by Laplace. It's called Laplace smoothing. This is from hundreds of years ago. The Laplace smoothing, or the Laplace estimate, is based on pretending that you saw every outcome once more than you actually did, right? So look at this sample here. We've seen the outcome red twice and the outcome blue once. The P of the probability of the Laplacian estimate of the probability of outcome X is defined by C of X plus 1, the count of number of times we've seen the outcome X, plus 1. We are pretending that we saw this outcome once more than we actually did, over the total number of observations, assuming that each have one more, has occurred once more than we've actually seen, which essentially translates into C of x plus 1, count of number of times we've seen the outcome x plus 1, over the total number of the total number of samples plus the number of possible outcomes. Now, for this example here, the typical estimation using likelihood estimate is the outcome of red is 2/3. We have 2 red outcomes in 3 samples, and the probability of blue occurring is 1/3. We have 3 samples, one of which is blue. What would it be if what would these probability estimates be if we were to use the Laplace estimate? So it would be C of x plus 1. What's the C of x? How many times what's the C of red? Well, we see red twice, it's 2. So 2 plus 1, let me write it down. For red, it would be 2 plus 1 over, what's the total number of samples? What's this n? It's 1, 2, 3. 3, what's the total number of outcomes? How many different outcomes are possible? It can be red or blue. Plus 2, which gives us 3/5. What about the estimate for outcome blue? Well, it happens once. Let me change the color. It happens once. So C of blue is 1 plus 1. Oops. Plus 1 over total number of samples, 3, total number of outcomes, 2, 5. So this becomes 2/5. Now, this is just a pointer to those of you who are more familiar with stats and probability. The Laplace estimate can be derived, or we can derive this estimate with Dirichlet priors. We are not going to talk about Dirichlet priors here. This is just a general hint to those who are interested in learning more about the foundations and the mathematical mechanics of Laplace estimates. Are we clear on how Laplace estimates are calculated? Any questions about this? One question is, so what's the point? Why would we want to do this? Any thoughts on that?
To achieve the accuracy,
How?
like
So the answer is already in your memories. Let's go back. Do you remember this slide here? Do you remember these absurd infinity values for these ratios? And do you remember why these values came to be infinity? It was because our probability estimate for certain words given ham was 0, right? Now, if we had applied the Laplace estimate method, no outcome, the probability of no outcome would have been 0 because it considers each outcome occurring at least once, right? So this way, we are getting rid of the division by 0 problem. Let me go back. All right. Now, the Laplacian the Laplace estimate method can also be extended by pretending that we saw every outcome k extra times. Instead of just one extra time, it can be an arbitrary number of extra times. The formulation would change to this form: P of the Laplacian estimate of an outcome x given k extra occurrences is in the form of count of the number of times the outcome x has occurred, plus k, remember we had plus 1, now we have plus k, over the total number of samples plus k times the total number of possible outcomes. Now, what's Laplace estimate with k equals 0? It's just a likelihood estimate, isn't it? It's C of x over n. So the likelihood estimate can be seen as a special case of the Laplace estimate. K is said to be the strength of the prior. How strong are we assuming the prior to be? So this is just a piece of terminology. Let's look at a few samples. What's the Laplacian probability distribution estimate of these sampled outcomes given k equals 0? So it's just a likelihood estimate. It's C of red. For red, it's, let me change the font color. It's for red, C of red is 2. 2 plus 0 divided by total number of samples is 3 plus 0 times total outcomes. So it becomes 2 over 3 for red. And for blue, it's 1 over 3. That's what we had before. Now, for k equals 1, we've already calculated this in the previous slide. It's essentially, we already have this, 3 over 5 and 2 over 5. What about k equals 100? What would this be? So it would be, for red, it would be 2 plus 100, 102, divided by total number of samples 3 plus 100 times 2 possible outcomes. It can either be red or blue. So this is 200 plus 3, this is 203. That's for red. What about blue? Who can tell me what the Laplacian estimate of the blue outcome should be? So how many times do we see the outcome blue in these 3 samples? Only once, right? So we just plug it in. 1 plus 100 gives us 101 divided by 203. Now, notice that the difference between these two has become much smaller in k equals 100 estimate. This is why we call using this estimate Laplacian smoothing. Laplace is smoothing. It smoothes out the probabilities by assuming that there are instances of each occurrence that we have not observed. Any questions about Laplace estimate and Laplace smoothing? Okay, let's move on. What about for conditionals? What if we want to estimate the probability of an outcome X conditioned on an outcome Y? Well, it's exactly the same. We just change the count of X to the count of X and Y occurring at the same time. And instead of this N, we'll then have the total number of times we've seen Y occurring, which should be straightforward, which should make a lot of sense. Speaking of sense, if we apply Laplace smoothing to the spam-ham classification problem, the values, we no longer see infinity. Why? Because we no longer have a division by zero. None of these probabilities are zero using Laplace smoothing. And the ratios are all countable numbers. Now, do these values make more sense than before? I think yes. But let's look at a few samples. First of all, what do these mean? Helvetica, Verdana. These should sound familiar to you. These are different fonts, right? It seems like it's more likely for a ham email to be written with Helvetica as its font than Verdana. And it's more likely that the font of a spam email be Verdana, at least based on the sample, the training set available to us. The word seem to be very likely to occur in ham rather than spam. On the other hand, the word credit seems to occur a lot more in spam than ham. And it makes a lot of sense. It makes a lot of sense, to me at least. What about you? Do you have any questions about the interpretation of what we are looking at here, or whether what we did makes sense or not? Are we clear on why we applied Laplace smoothing to this problem? We wanted to get rid of infinities, right? We wanted to get rid of infinities caused by division by zero, which was a result of assigning zero probability to some of our estimates. Now, this is important to keep in mind. For real classification problems, smoothing is critical. Accounting for unseen instances is critical. Is critical for what? For achieving better generalization. That's what it's critical for. If you want to be able to generalize better, you need to apply a smoothing or regularization to account for unseen samples. Now, let's talk about tuning. Remember we talked about hyperparameters and tuning hyperparameters on held out or validation data, right? We've got two kinds of unknowns. As machine learning designers and engineers, we're dealing with two kinds of unknowns. The first kind are, of course, the parameters of the model, like the probabilities of features conditioned on labels or the prior over labels. But there's another kind of unknown that we have to deal with. And those are the hyperparameters, the parameters of the design of the model. And these are determined by us. These are design choices that we determine. What are examples of hyperparameter? Like one example is the amount or type of smoothing mechanism or smoothing technique. Are we going to apply Laplace smoothing? If so, that's a design choice. If so, what should be the K value, the strength over priors in Laplace smoothing? Or if you're dealing with learning rates, we'll talk about learning rates again in the next lecture. What should be the learning rates in our model? These are choices that the designer makes. These are choices that are made under the structure of the model and the training algorithm. That's why we call them hyperparameters. So what should we learn here? We learn the parameters, these parameters, from training data. Then, to figure out the best choices of hyperparameters, we tune our choices on a different set of data called the validation set or the held out set. This is because if we use the same training data for hyperparameter tuning, it becomes really messy to tune both the hyperparameters and the model parameters at the same time. Later on, we'll do a more detailed discussion over this. For each value of the hyperparameters, we need to train and then test the performance of the trained model based on the hyperparameters on the held out data. Then we choose the best value for each of the hyperparameters and do a final test on the test data. This is the more detailed version of training phases. First, we train on training data. Then we test the trained model on validation or held out data to tune the hyperparameters. Then we go back to training and train again with the new hyperparameters. Then we test on the held out data again to see how well the hyperparameters are doing. And in the end, we choose the best value, the best choices and values of hyperparameters and do a final test on the test data to see how well the final model performs on unseen data. Any questions about this? All right. So we haven't talked about features much, and we aren't going to in this lecture. The next couple of lectures are going to be full of discussions over features and how to construct different features. But featureization and feature engineering used to be, is, and continues to be an important part of a machine learning engineer's job. Coming up with good representations of the data is a very, very crucial part of machine learning. We'll talk about this in more depth in future lectures. Now, what about errors? If you ever see that the performance of a machine learning model is reported as 100% accurate, you should immediately doubt either the honesty or the proficiency of the report writer in machine learning. Machine learning models are very unlikely to be 100% accurate. There will be errors. Errors are almost inevitable in machine learning. How do we deal with errors? First of all, let's look at two examples of errors. These two are samples of emails. One of these is ham, the other is spam, but our models, our best models may incorrectly classify the ham email as a spam and the spam email as ham, right? This is an example of a very common example of the type of errors that may occur. What do we do about errors? Well, there are a few approaches, there are a few techniques or strategies that can be used to reduce the number of errors. One of the most common strategies is to change the feature representation. If we are seeing too many errors in our model, we may need to add to the number of features we are using to represent the data. For example, in spam classification, maybe just looking at words and word counts is not enough. Maybe we need to look at some other features like, have you emailed? Has the recipient emailed the sender before? Or is the sender in the contact list of the recipient? Have one have many other people just received the same email? If so, there's a very good chance that that email is spam. Is the sending information consistent? Is the sending mail server consistent with the email address? For example, if somebody's emailing you from Microsoft.com, did the originating server belong to a Microsoft network? Is the email in all caps? We've already talked about this as a feature. This was suggested by some of you as one of the potential features. Do inline URLs point where they say they point? This is mostly for detecting phishing attacks. Does the email address you by your name? If so, it's less likely that the email is a spam. So we can add more features to make the model more accurate. So in the Naïve Bayes model, these information sources can be added as new variables, as new random variables of the evidence in the Naïve Bayes model. In the next class, we'll talk a lot more about classifiers, and we'll specifically talk about classifiers which let you easily add arbitrary features, and later we'll talk about deep learning models that induce new features or allow us to easily induce new features. Is this the only thing available to us? Is this the only method available to us to reduce errors? No. There are many other approaches. For example, maybe we just don't have enough data, or maybe our data set, our training set is not representative. Maybe we just need to collect more samples. What else? Well, smoothing can help. Anything else? Regularization can help. We'll talk more about regularization in the next lecture. There are other approaches, but these are the main ones that come to my mind. Now, how do we measure the performance? How do we know how well our model is doing? Other than metrics such as accuracy, we can compare the performance of our model to certain baselines. So what are baselines? Baselines are very simple strawman procedures. They help us to determine how hard the task is, and they help us to know what a good accuracy is, and it helps us to understand how much better our model is performing than simpler or previously created models, whether what we've done is worthwhile or not. One type of baseline is the weak baseline. For example, the most frequent label classifier. What does this baseline do? This baseline model essentially classifies everything as the most frequently occurring class. It gives all test instances whatever label was most common in the training set. For example, if we apply this to spam filtering, it labels everything as ham. Why? Because we had 66% ham data and only 33% spam. The most frequent label classifier only assigns the most frequent label to every entry. Now, the accuracy may be high if the problem is skewed. If the data set is highly imbalanced. For example, calling everything ham gets 66% accuracy. So if our classifier, if a Naïve Bayes classifier that we've spent time on training and tuning gets 70%, it's not very good. It's not doing much better than a very simple most frequent label classifier. Can you think of any other simple baseline classifiers that we can use for measuring how well our model is doing? Any thoughts? Any ideas? How about a random model? a model that assigns labels based on coin flips. So 50% of the time, the label is going to be ham, 50% spam. That's also a weak baseline, and some use it to show their model is doing much better than random, but it doesn't tell us much. Unless the accuracy of your model is less than 50%, in that case, you can say, hey, our model is doing worse than random. In practice, we mostly use previous work as a strong baselines. For example, we look at the state-of-the-art deep learning spam classifier that's available to us, and we compare the performance of our new model to that state-of-the-art baseline. This is, as I mentioned, called a strong baseline, and it helps us understand how much improvement our model is providing compared to what's already available out there. Any questions about baselines? Are we clear on the point of baselines, how baselines can help us, and different types of baselines? All right. Now, this is the last topic I'm going to talk about today, and it's the confidence of a classifier. If you have a probabilistic classifier, like, let's say, Naïve Bayes, which gives you the probability of the occurrence of each outcome or each class, given the evidence, the confidence is, the confidence of that classifier is essentially defined as the posterior probability of the top label. In other words, the confidence of an outcome X, for example, spam, is the max over label of how likely it is the outcome being Y over the sample X, over the input X. So given an email X, the confidence of the model is the maximum probability assigned to any of the classes. For example, the probability of the email being ham, let's call it PH, can be, after passing it through the model at test time, can be, let's say, 0.7, 70%, and the probability of another Y is a spam can be 0.3. So the confidence of a probabilistic model, this probabilistic model, for that particular email is essentially 70%. It represents how sure the classifier is of the classification. Any probabilistic model will have confidences. Why? Because they all have P of label given inputs. There's no guarantee that the confidence is correct, right? The confidence may actually be incorrect, but it gives us some sense of how confident the model is in making its decision. Now, there's also the process of calibration. In a weak type of calibration, higher confidences are assumed to mean higher accuracy. In a strong calibration, the confidence predicts the accuracy rate. Now, what's the value of calibration? We will talk about this a lot more in the coming lectures. So let me summarize what we talked about today. We saw that Bayes' rule lets us do diagnostic queries with causal probabilities. We talked about the naive Bayes assumption and how this assumption essentially assumes that all features are independent given the class label. We saw that we can build classifiers out of a naive Bayes model using training data. We talked about smoothing and the importance of smoothing estimates in real systems. And we touched upon the classifier confidence measures and how useful they can be. Very well. We are done with the lecture today. First of all, does anybody have any questions about any of what anything we talked about today? All right, so I'm going to post the slides as well as the reading material for this lecture and a practice problem set today. I will be posting a Gradescope quiz probably later today or tomorrow. It will be due next week before class time. If you have any questions, if you need to discuss anything, if you need more resources or information about anything we talked about today, come to my office hours from 12 to 1 p.m. every weekday, Monday to Friday, or send me a message on Slack or send me an email. It's very important that you understand what we talked about today before we start our next discussion. Everything we talked about today forms the basis of our final topic, which is going to be on machine learning using perceptron, logistic regression, and neural networks. Very well. Thank you very much. I'm